to comment, please press *6 to mute and unmute, and *9 to raise hand. Public comments will be taken during the public comments section, agenda item number 3. If you want to submit a technical question related to the topic of today's discussion during the Q&A session, please submit via chat. In-person attendees must fill out a card for questions. This meeting will end at noon. Now, I'd like to introduce the Saltwater Water Management District Executive Director, Drew Bartlett.
Thank you, Yvette, and welcome everybody to our Water and Climate Resilience Metrics Workshop. The one thing we take very seriously at the South Florida Water Management District is science and data and analysis. And, soon after, actually we've been working on it for a while, but soon after we hired our District Resiliency Officer, Dr. Carolina Moran, we put our sights on measurements, data. How do we measure and understand the changing climate, changing water conditions in South Florida Water Management District? And we're happy to bring today to you some of our efforts and our work related to that, and certainly encourage any kind of public participation and public engagement as we share our knowledge and share our data with you through this workshop. I'm very excited that we do have a couple of guests that we're welcoming today. We do have the Deputy Secretary for the Florida Department of Environmental Protection. His name is Adam Blaylock, and he has come down here to help us with this workshop, and he supervises the Office of Resiliency and Coastal Protection, which implements the statewide resiliency plan for the Florida Department of Environmental Protection. So I'm happy to introduce Adam Blaylock.
Yeah, thank you very much. I'm really excited to be here. Since taking office, Governor DeSantis has been very focused on resiliency and coastal protection. In one of his first days in office, under executive order, he established the Office of Resiliency and Coastal Protection just for that purpose, and to address and have the department begin addressing the impacts of sea level rise and protection of our coastal communities. Along with that, also supporting the department's efforts in implementing the slip study legislation that passed, and the department establishing of kind of a one-of-its-kind slip study tool where any public constructed building has to do an analysis to address and provide possible options for being more resilient against sea level rise across the state and the coastal building zone. And then on top of that, most recently last session, signing Senate Bill 1954, which was a big resiliency piece of legislation that has been on the forefront of adopting plans, vulnerability assessments, and identifying projects to help address the impacts of sea level rise and flooding on our coastal communities. And we're very excited that we recently announced the first 3-year flooding and coastal resilience plan, which funded over 76 projects, totaling over $270 million. And we're also in the process of finalizing project lists for the additional $500 million that was appropriated through the ARPA funds this past session. And so with that, the department, we're very excited about all the efforts going on and identifying projects. And one thing I'd like to do real quick beforehand is also acknowledge the new staff that has come online at the department in the Office of Resiliency and Coastal Protection that has been integral in helping put the plan together, identify the projects, which took a lot of time and effort going through all of the projects that were submitted. And just to introduce those people, the program administrator for that office is Diane Quigley. The director is Alex Reed, and Eddie Boza, who is our planning and policy administrator, along with Joshua Lugo, who does all of our GIS and identifying different projects locations so that we can see what the project impacts are and how they're benefiting to protect on sea level rise and resiliency. And then our grant manager, Hannah Tillotson, who's also overseeing all the grants once they get developed and in place. And so this team has come together quickly after the passage of Senate Bill 1954 and has done an excellent job in putting this first plan together. As we continue moving forward, we're also, the governor in his most recent budget put forward an additional $500 million on top of the over $100 million that goes in recurring funds under the dock stamp revenue. So looking for an even larger use of resources and being able to identify even more projects to expedite the being able to address the impacts of resiliency. So very excited about being here today and listening to the workshop and providing any help that the department can in doing that. And also we'll be doing our rule development for implementing Senate Bill 1954 for establishing some more specifics on the criteria for selecting projects and ranking and scoring based on what's in statute. So we hope the public to provide support as we move forward with that workshop, and also the district. And so just happy to be here and appreciate the opportunity to speak. Thank you.
Thank you, Mr. Blaylock. It's also my pleasure to introduce our newly minted statewide Chief Resiliency Officer, Dr. Wesley Brooks, who also is joining us today to have a few remarks. So, Dr. Brooks.
Thank you, Drew. Are you all able to hear me okay?
Yes, sir.
All right. And I can't get the video to come on. I think it's on y'all's end.
We hear you. So, but I don't think there's going to be a video of you.
No worries. And I'll just get going. Thank you. And obviously, Drew, thank you for hosting this alongside the governing board. And I just want to put out a special note of appreciation for Dr. Carolina Moran, who's leading these efforts to promote resilience across the district's operations. For those of you who don't know me, my name is Wes Brooks, and I have the privilege of serving as Florida's Chief Resilience Officer. You know, resilience at its most basic level is about deciding what's worth protecting and figuring out how to do so in both the least obstructive and the most economical way. Of course, to even get to that point, you know, we need to understand what the risks that we face are and how potential impacts might threaten whatever, you know, our final interests in protection are. And that's where fundamental science is really critical as we look to evaluate risk and plan to mitigate potential impacts. I'm really excited to be here today to hear more about how the district's science is informing the new opportunities for us to literally rise above the challenges facing South Florida's 20th century flood control system. And especially now that we are, yes, well into the 21st century. And really, Florida is fortunate to have a governor right now who is meeting the moment, who understands that we can't wait any longer to confront the reality of sea level rise, of changing precipitation patterns, of a larger share of our population potentially in harm's way than ever before. And beyond just saying the right things, as Deputy Secretary Blaylock mentioned, he's doing the right things too. Governor DeSantis is committing unprecedented investments to promote a more resilient Florida. I was proud to stand with the governor on the shores of Tampa Bay just over a week ago as he announced the first statewide flooding and sea level rise resilience plan project list. Those first projects will begin implementing real solutions for our inland and coastal communities. But that's just the beginning, and we have a lot of work in front of us. We have to ensure that all of the state's resilience efforts, including the statewide plan and the related Resilient Florida program, are carried out in partnership with all capable entities, like the South Florida Water Management District, to maximize the return on the state's investment and enhance benefits to our local communities. I will say that I'm confident that the district's science puts us in a better position to capitalize on the leadership the governor has exhibited. And as a result, and consistent with its unique history and its hopeful future, I think South Florida will continue to be a place defined by human adaptation. Thanks again to everyone for being here and for everyone's efforts to work together to seize the opportunities before us.
Thank you, Dr. Brooks. Great words. I really appreciate it. Now it's my pleasure to turn it over to all the smart people sitting in front of me that do all the work behind the scenes to put us in our position to address our changing climate, sea level rise, and adapt to our future conditions. So at this point, I would like to turn it over to Dr. Carolina Moran, who will guide us through this workshop today. Dr. Moran.
Thank you, Executive Director Drew. Thank you very much, Deputy Secretary Adam, for coming here today. And thank you very much, also Dr. Brooks, for joining us this morning. Yes, we are here today to talk about science. And this is really exciting. This effort initiated back in June last year, 2020. Something interesting to tell you is I got to meet two of the experts that are joining this team only when we did the dry run early this week. So we were advancing a lot of the science remotely using all the support that we got from the district to work through all this time. But really, after more than 1 year working with these people here, I got to meet them in person, and it was really great to get this chance this week. And it's an honor to be working with all of you. So yes, we did this effort through an internal work group. We had several meetings. We had then the availability of technical leads that are leading each of the metrics that we selected to be part of this effort. We also launched a draft report early this year, and we sent it out for public comments. We received a very extensive list of comments that we have been addressing through this year to be able to incorporate not only to a report, but really towards the implementation of what we are bringing to you today. So we have really robust products that are already implemented, following a lot of the recommendations, the comments that we received early this year. And we are really doing that through a deep science-based approach, really focusing on also, I believe Dr. Brooks talked about what are the goals, what do we want to protect? And we as an agency here, we as the district want to protect our mission. So it's a very focused approach on water and climate that are related to what we are doing here today. And we have two major outputs that are going to be introduced here too. We have our hub, our metrics hub, that we are going to be hosting this data, some of the science, some explanation in a format that is more to communicate with the public and engage. And we also have a technical document that we're going to be introducing today as part of the South Florida Environmental Report. So just going a little bit back to this year on what we saw in terms of extreme events in South Florida. It was a fairly less intense king tide season, not really significant tropical cyclones contributing to more intense swells along in the Atlantic Ocean near the coast of the Florida, as well as our Gulf course. But even though we had the third most active hurricane season this year, we exhausted the names 2 years in a row, again, this in 2021. And we did have impacts from extreme rainfall. Dr. Wes also pointed to the rainfall, changing in rainfall patterns as part of what we are trying to do. And yes, we saw some extreme rainfall events happening this year. We have some pictures here from downtown Miami in November. We have also king tide combined with some rainfall in Palm Beach in October. So it's still, we are documenting and tracking what's happening here. A glance to what happened in 2020, definitely a more, I would say, intense year, eventful year. We had Tropical Storm Eta. We had the king tide season, a very intense, significant with record breaking in some of the days during the 2020 king tide season. We had Hurricane Isaias, and we had a very huge rainfall event that happened in the Memorial Day last year. And we talk about that. We went through that extensively in our first workshop, but just to help us to understand this. And this is really what we are doing with this effort. So what we try to understand is how significant was 2020? How significant was 2021 compared to the record? But just not the average, like what are the impacts that we are observing from those larger events in South Florida? How can we truly associate with science facts these events with climate change? And are these events really part of a long-term trend? Sometimes we can make the assumption, yes, this is part, but we are here to really try to read that and try to make the associations that we need to scientifically say, yes, these events are part of a long-term trend or not, and how can we help to explain all of that? Going back quickly to the objectives of this work, I think we talked a little bit, but we really want to track and document long-term trends and shifts in our observed data. Our agency has a very long tradition in managing this large amount of data that we have, and also making these observations available for the public in general. We have those in our DB Hydro for many years now. There's the solid data, there's the science data that we use there. So we really want to use this data. There are other agencies nationwide doing similar work with nationwide data, but we do have our data that we are looking at, and we are really working on doing this, advancing those data analysis. We also want to understand then this, using this data and this analysis, really advance the understanding of those impacts, the climate change impacts over the district mission. Report and communicate. I talk about the hub a little bit. We have the goal to not really do the science, but make this in a way that is easy, that people can understand, and we can communicate a little bit what we are seeing, and also any of the assumptions that we do along the way, and support the assessment of future conditions. We have significant planning efforts in this agency that we depend on looking at the future, and we have to account for changing sea level, for different rainfall patterns, and some other assumptions. So we need to be able to have this data to support our planning processes. Some of the benefits that we see is really, as I mentioned, a stronger planning capacity by documenting and publishing those observed trends district-wide based on the best available science, really substantiate our modeling assumptions and risk-informed operational decisions. We have the need, and we are identifying like really robust infrastructure investments, and we need to make smart decisions here that would be supported by robust assessment of current and future anticipated conditions. We want to engage with our partner, local governments, partner agencies, so we want our community to really be educated and informed on those aspects. And also we want to enhance the resilience overall of our projects regarding what we see and what we are expecting. So yes, and the focus of all of that is our mission. I talked a little bit about that. So we have here our 3 mission elements: flood protection, water supply, and ecosystem restoration. And the goal of looking at those metrics is really to allow us to see how they can be impacting our mission. So one interesting aspect that we were able to also elaborate and discuss as we were evolving with this effort is that we do identify some of those metrics that are really primate drivers of a change. We're calling them the climate metrics. They are like changing rainfall patterns, the increasing tidal elevation, sea level rise, and also evapotranspiration changes. And a lot of our metrics are also metrics that we are calling now resilience metrics. So those are beginning to show the consequences of those changes, like cascading drivers that also impact our missions. So we have water quality impacts, saltwater intrusion, increasing salinity in the estuaries, soil subsidence, estuary, wetland migration, flooding, and wet season increase in groundwater levels. So this is really a summary of the set of metrics that we decided to evaluate as part of this effort. That's where we departed from. And this is also what we're going to find in our internal work group final report. So at this point, the report mostly documents how we got to this point. We address all the comments that we received through the way. And we have a document that basically tells what we did this past year. And as I said, on top of that, we have then the data and the science. So you're not going to really find the data in this report. This is more like a process. And then you're going to be introduced to where you can find it and where you can navigate to get the data and additional information that was produced as part of this. I like to highlight one of the comments that we receive here. We appreciate the partnership that we have with the USGS, but they really emphasize that we have a comprehensive and insightful review of the available data that will help guide the South Florida Water Management District in many of the critical directives along the really long term. We pull a lot of information together, and providing this, the data analysis will make this document available not only for the district, but for many of the stakeholders and other water resources managers in the region. And it can really serve as a template for other agencies or water management districts, really importing the data and the analysis need for long-term planning under those changing conditions. With that, I'd like to introduce Nicole. She will really bring us to those major outputs that we have today and summarize. So thank you.
Thank you, Carolina. Good morning, everyone. I'm very happy to be here today to share with you how we're advancing resiliency efforts in our region and how we're doing that specifically through the implementation of the district's water and climate resilience metrics. As Carolina explained, the phase 1 long-term observed final report of the water and climate resilience metrics really explains an approach of how we analyzed data. And what this approach produced is a report that is essentially a baseline study that will provide a historical context from where our resilience metrics will evolve. Today, we're building on that effort by bringing resilience content to the SFER, the South Florida Environmental Report, and through the development of the District Resilience Metrics Hub, which is, has been made public and available today. Together, these next steps will advance our understanding of the impacts of climate change in our region. The South Florida Environmental Report is home for scientific discussions. So it is here that we will explore the significance of the current observations each water year relative to the trends that we identified in the historical record, and where we will feature major highlights, new insights, and shifts that are observed in our region each year. If you would like to know how the resilience metrics are evolving and what extreme events impacted water management in our region each year, Chapter 2 is the place for you to look. Chapter 2 in the environmental report is the new home for resilience metrics content beginning in 2022. Chapter 2A will feature the same content that has been featured historically in Chapter 2 in past years, with the addition of summaries for major events of the water year. These are events like the ones Carolina mentioned in 2020, the Memorial Day event, tropical storms, and king tides. We bring information and a summary of these events to really memorialize the key aspects of the water year that explain why water management may vary each year beyond isolated event reports that our technical staff produce. In the upcoming environmental report, Chapter 2B is the continuation of the phase 1 efforts and picks up where that final report left off. In future years, the South Florida Environmental Report will feature information about all of our metrics, the ones that Carolina shared earlier with you. In 2022, you'll be able to read about rainfall, evapotranspiration, tidal elevations at coastal structures, and a set of water quality parameters. The Resilience Metrics Hub, the link is available here on this slide, which we'll share with you shortly after this meeting adjourns. This is the other major output that we're excited to share with you today. It is imperative for us that we document our findings and also prioritize sharing the latest research advances in resilience with our partners and with stakeholders. The Resiliency Metrics Hub is designed as a living hub. It is a place where we can modify data regularly and update and bring new information to the public. It offers us flexibility to add new and different kinds of data in the future. When you look at the hub today, you will see story maps for a few selected water and climate resilience metrics. Story maps are interactive tools where you can explore both data and information together. We started these metrics because of their more static nature. And in the future, we will also use story maps as to complement our more dynamic metrics as we bring in live and automated data. All of these efforts were made possible from the support of our technical leads and the various teams across many business units throughout the district. I would like to introduce next one of our technical leads, Her name is Corinne Smith. She'll be talking to you about observed trends in groundwater.
Thank you. So I'm going to be speaking about groundwater stages and saltwater intrusion along the coast. When you look, as Carolina explained, climate metrics can monitor actual climate drivers like rain or sea level, or they can monitor things affected by those drivers. And the resiliency metrics that I'm working on are the ones that are impacted by sea level rise and changes in rainfall. And we're looking at groundwater stages and aquifer salinity. Saltwater intrusion. The other issue, though, is that saltwater intrusion can also be influenced by human activities such as groundwater pumping and drainage canal operations, which can complicate determining just the climate impacts. So why are we doing this? Well, if the saltwater intrusion metrics show that we are able to slow the inland movement of the interface, it lets us know that we are managing toward a more resilient system. So just kind of 101, what is happening with sea level rise? And sea level rise, the sea level water is denser than the fresh water that is sitting atop it. And as sea level rises, it pushes the salt water further inland at the base, and that also pushes up the fresh water that is floating on top of it. And what happens with that is then there can be inland flooding because now the water table is being pushed higher up. And then also we can, there's a Geibin-Hertzberg ratio that tells us that for every foot of fresh water above sea level, there will be 40 feet of fresh water in the aquifer below sea level. So as we push up this, we are having less fresh water head above sea level, and this can cause salt water to come in and into the aquifer. So how do we look at it? What do we do when we see the monitoring data? There's different ways of it. These are called induction logs. These are done by the United States Geological Survey. And each line on these plots is a conductivity measurement for a particular year. The black line is the most recent year. And it shows, these kind of show you two different ways that the aquifer, the salinity comes into the aquifer. One is on the left is the classic, where it comes in at the base because it's denser water. And as you can see over the years, it's getting at the base of the aquifer, it is getting more and more saline. On the right, you can see, oh, I have a pointer now. Okay, thank you. On the right, we're seeing that there is salt water coming into the aquifer at a lot of different levels. And sometimes this is because there's more porous parts of the aquifer, and so the salt water can come into those areas more easily, or it may be because there's pumping. And as you can see here, there's the black line shows that it's actually gotten fresher here. It actually was more salty in the past. And so what that kind of indicates is maybe it's a well field where they've cut back on pumpage because of the salt water coming in towards their wells. And in backing off in their pumpage, they're able to keep it fresher. Another issue, another way to look at it is these cross sections that are done by looking at monitor well data. This is on the West Coast, and on the West Coast of Florida, it's a little more complicated because we have multiple aquifers with confining units between the aquifers. So saltwater can move in at different distances in the different aquifers. And so we have to monitor more than one zone, the different aquifers. So if we want to look at a bird's eye view of that kind of data, what we're looking at here is how far in is the saltwater in looking from a bird's eye view. And the red line is the most recent one that we did, which was in 2019. And at the district, we do update these lines around our coastal boundary every 5 years. And so what we're seeing here, this is Broward County, then the green dots are all public water supply wells. So we're kind of keeping track of how is the front moving and how close is it getting to the wells. And when I took a look back over the last 20 years, I found that might not have caught all of them, but these are just a list of wells that have been abandoned due to saltwater intrusion issues. And so then we look forward in our water supply plans to see, well, who is at risk and do we need to work on projects for public water supplies to help with saltwater intrusion. And what we found in so the table on the bottom is the most recent results of all the utilities that we look at in our water supply plans, and then which ones are being threatened by saltwater intrusion where it's getting close. Some of them most of them have an alternative, like a well field further inland, or some deeper wells that aren't affected by saltwater intrusion in the Floridan aquifer, but some of them don't have that. And so those are the more vulnerable ones that we are looking at and working with to come up with options. So we have a lot of monitoring data, and the map on the right shows you that. There's the monitoring data that's in blue is actually sampled by the South Florida Water Management District, the blue dots. The USGS is the green dots, which is very significant on the coast. And that data is available in their own database, groundwater mapper. So those are wells that we are not going to provide a duplication of that data in our hub, but we will have links to get to the data in their hub. And then the yellow dots are water level and water quality data that we receive through our permitting requirements. And this data is data that's been available just in paper, but now we're taking a select group of these wells and we're putting them out on the hub so that you all can see the data that we see that we use in making decisions in our permitting process and our planning process. The well on the right just shows you a typical groundwater monitoring well which has got, it has a SCADA system on it and powered. And so we have real-time data on some of the wells in our system. So one of the things that we were looking at was how far inland is this rise in sea level happening that I showed you on the first map. And, as the sea level comes in, it pushes the water up. And do we actually see that in the data itself? So the light blue on the bottom is the downstream stage at a structure this is the Hollywood area. And I'm going to back up a second. This is the Hollywood area. And there are 4 wells kind of in a row from the coast inland. And there's a structure a little bit further south that's right in this vicinity. So there's 2 wells that are near or west of I-95 and 2 wells that are east of I-95. And they seem to group. So the light blue is the downstream structure, which kind of shows you tidal stages. And it's risen. There's been about a 1/4 foot increase over these 45 years of data that we have here. And you can see in this blue dotted linear line, it's just gradually getting higher and higher. And so now the water levels, the mean sea level at that station is above 1 foot. And obviously because it's tidal, it's moving around and seasonally. And then the 2 bottom lines here are the 2 wells west of I-95, and there, as you can see, they're gradually increasing in water level also. And the 2 top ones are the ones east of I-95, and they are actually they're increasing more. The the lower ones have increased a half a foot over that time period, and the two that are further east have increased 3/4 of a foot in general over that time period. So we are seeing that the sea level rise is affecting the water levels along the coast, and we're going to identify more of these lines of wells or put some in other areas so that we can keep an eye on how this is happening within our system. One of the other things that we're doing is that we look at the Biscayne Aquifer. It's our source of shallow groundwater for the whole lower East Coast. And we have a minimum aquifer, a minimum water flow and minimum water level prevention strategy for this, because the goal of the MFL is to make sure that we don't have, to try and slow or prevent further inland movement of the saltwater front to the extent that it would impact existing users. So one of our prevention strategies is to set up minimum water levels upstream of all of these salinity control structures, and there's 11 of them. And we look at the data, and the way the prevention strategy is set up is that it says that the water level upstream of each of these structures needs to be above a certain level for each structure more than half the year. Because we found that if it's below that for more than 180 days, the saltwater comes in and it's a lot harder to flush it back out. So when we set up these minimum levels in 2000, like 21 years ago, we looked at, what would be preventative. In this particular, we look at all of them. Okay, let me go on to the data. So this is an example of one of them. It's down in Snapper Creek in Miami, where the sea level is rising significantly. When we started out, we had a preventative head of like 2 feet. That's what was kind of identified in the MFL. So the MFL line is this green line. So the water levels should be above that green line for at least half the year. And then this is actually the downstream level of the structure is the gold. And so that's and as you can see that as sea level has risen, the difference between the freshwater and the saltwater, which 2 feet is preventative for like 80 feet of aquifer thickness, it's getting less and less able to, the saltwater, the sea level is getting higher and higher. And so our difference between our freshwater and saltwater head is not as preventative. So we're keeping an eye on this, and we're also looking to see in our water supply plans, we look at these MFLs and we determine if we need to make adjustments or what we need to do to make sure that they're successful. And with that, nope, I got one more. Okay. So we have a story map for all of the information that I just told you about. You can see more about it and write-ups on it. Those cross sections, the MFL maps, the monitoring data is all in our story map, which you can get to today. And this is just kind of a screenshot of a little piece of it. And with that, I would like to turn it over to Kevin Zhu, who will talk about evapotranspiration.
Thank you, Corinne. And good morning, everyone. My name is Kevin Zhu with Hydro Data Management Section and an HNH Bureau here in the district. Today, I'm going to give you a brief review on the observed trend in evapotranspiration. As its name indicates, evapotranspiration includes 2 parts: the evaporation from the ground surface and then the transpiration from plants or wedges. In a hydrological cycle, there are 2 most significant components: rainfall and evapotranspiration, or ET. The ET rate within the United States, each year on average about 2/3 precipitation returns to the atmosphere through ET. And then the ET rate is highest in the southeast, where the Florida is located. Here on the chart shows a side-by-side comparison of average monthly rainfall and potential ET over the past 25 years at the district. The blue column indicates the rainfall, and then the yellow one indicates potential ET. We usually break a year into wet season and dry season based on rainfall amount. This is based on rainfall amount. So the wet season is from May to October, 6 months. And the dry season is from November to next April, also 6 months. So if you look at the dry season, the rainfall of the dry season usually just around 2 inches per month. And if we move up, this number move up to 4 inches per month, we can find May and October. This is the beginning and end of the wet season. But sometimes we also call transitional months. And continue to move up to 7 inches per month or greater. We see in the real wet season or in the raining months. This is the June, July, August, and September. However, if we look at the difference of the ET minus rainfall, it gives us a different perspective. Here, the monthly differences show at the top of the month. Here, this one. So you can see we have a shorter wet season and a longer dry season. The biggest change here is in May. We may start to see more rainfall in a year. The ET rate also picks up in May. So here the difference in May is on the dry side. And for the October, if you can see the difference, is just near 0. So in terms of the water balance, the October is a neutral month. During a drought, the significance of ET is magnified as it continues to deplete the remaining water in the already dried water body or in the ground or in the soil. Before a trend analysis, we set 2 criteria for data selection. The first one is a period of records 25 years or longer. Because if the record is not long enough, the trend doesn't show up, or the result is not reliable. And the second criteria is we want the station still in operation, so we can continue for the future trend watch. Not so many stations fall in this criteria, but fortunately we found 3. And 2 of them are about pan evaporation, and 1 is about the potential ET. Here you see in the first big chart, at the top, the green line, the station is called WPB EEDD. This data is from city of West Palm Beach. And then the station is just by the East Coast. The second one in the middle, the data is from the station S7 pump station, which is maintained by our district staff. And then the third data set at the bottom, the blue line, is from USGS. Actually, it's through a research project with University of Alabama. And this data set is about the potential ET. And all these 3 data sets, they collected or estimated independently. when they collect the data, they don't know each other, the others' work. So we can use it to do a cross check. And as you can see visually, these 3 data sets show an upward trend. And also their slope of change is quite similar, around 1/4 inch per year. And this trend from these 3 data sets are all proved by a statistical test. It's called the Mann-Kendall test. And it shows statistical significance at 5%, or sometimes people call 95% confidence. The second small chart here shows more details from the data at the S7 station. Since S7 has the longest period of records back to 1961, which is 60 years ago. And it's also the best, probably the best maintained station in the field. Okay, as you can see here at the top, this is not all still the annual data points, but it's divided to 2 groups. This orange dot and this green dot. It was separated at the year 1985 because we changed the monitoring schedule in that year. Before we give the data every day, but after we only measure the data on work days. But you can see here, they have different slope of change, but they both show an the upward trend. So indicates probably the measurement change didn't impact the data quality. At the bottom portion of the chart, this shows the data of season, the dry season and wet season. Wet season indicated by the blue dots, and the dry season by the brown ones. And they both show upward trend, but for wet season, we see more variation, but in the dry season is more stable. This is another presentation of an S7 data. This is the monthly values over the 60 years. It's in the green column, indicates the monthly value. And we also did frequency analysis, which is given the 10-year return is in the blue column, and then the orange ones is for 25-year return. Trend analysis also showing here is in the dashboard green line. And then this is the slope of change based on the maximum monthly value in a year over the 60 years. And you also can see a clear upward trend. So after seeing the trends from the data, we started to be curious about the driving factors or causes behind this trend. And we did some investigation here. In hydrology, it's well known, people aware about 4 parameters usually contribute to ET most. They are solar radiation, relative humidity, air temperature, and wind speed. And then the data show here in these 2 charts, the period is from 1995 to 2020. And most of this data is from district weather station. We also get one data set from USGS, which is in the solar radiation, which is in the pink one here. I use the sign plus indicates upward trend, and then the minus indicate a downward trend. And then the size of the sign indicate the relative significance of the change. So once we link the environment variables to the ET data. And we see the correlations here. Also use a similar sign to indicate how high or lower the correlation. And we see here is most correlated with ET is solar radiation. The second one is relative humidity. Why we don't see much from the air temperature and the wind speed. So with all this information displayed, and we believe the South Florida has been seeing an upward trend, ET, that we can track back to 60 years ago. And then the average change ratio, the change rate is about a quarter inch a year, or about 6 millimeter a year. And then the major driving variables behind this trend, the first one is the increasing solar radiation, and then the second one is the declining relative humidity. So this is my latest update on the ET trend analysis today. And thanks for your listening and the interest in this subject. Our next presentation will be given by Nanette Irakonen. He will talk about the trends in water quality.
Good morning. Thank you, Kevin. This morning, I'm going to go over our preliminary trend analysis for parameters in the water quality metric. The selected parameters are routinely measured by the district and are expected to be good response variables to climate change. Results presented will highlight some of the challenges in differentiating the impact of climate change on water quality from other influences such as land use, hydro management, and other anthropogenic activities. It is important to understand that the district's water quality monitoring program was not designed to track changes in climate. So for our analysis, we used 48 years of temperature, dissolved oxygen, pH, and specific conductance data. The water quality data was retrieved from the district's corporate database, DV Hydro, for 6 stations located in Lake Okeechobee. These stations were chosen because of their long monitoring history, and data for each parameter were aggregated as monthly means. Trends were determined using a seasonal man-Kendall test, and an interpretation of the observed trend for specific conductance was explored. So this plot shows you the 3 water quality components, temperature, DO, and pH. And the shaded regions, I just want to orient you on the plot. The shaded regions indicate drought years, while the red arrows show hurricane events, and the yellow arrows, which are probably not visible as yellow, show the tropical events, the tropical storm events. The top plot shows water temperature. Now, water temperature is an important parameter because it regulates both biological and chemical reaction rates in water, and it is influenced by solar radiation and heat exchange with the atmosphere. The middle plot shows dissolved oxygen levels. Oxygen levels are affected by water temperature. pH is shown in the bottom plot, and pH will vary with changes in dissolved oxygen as well as rainfall. As you can see from the plots, All three parameters exhibit seasonal patterns. Over the 48-year period, temperature and pH data show an increasing trend. However, neither one of these trends is statistically significant. In contrast, dissolved oxygen shows a statistically significant decreasing trend. However, the annual rate of change, which is represented by the sun slope, is so small that it's not measurable over the period that was analyzed. Our next plot shows the time series data for specific conductance in the lake. And one of the things that we discovered was a measurable and statistically significant decrease of this parameter over the 48-year period. There was a 40% decrease in specific conductance from 1973 to 2020. Initially, the specific conductance levels were atypical for what you would observe in a Florida lake. But by the end of our period of record, those specific conductance levels approached the typical level of approximately 400 microsiemens per centimeter that you would associate with Florida lakes. Specific conductance is affected by the types and amounts of ions present in solution, and it's influenced by evaporation and precipitation. Higher levels are typically associated with droughts and dry seasons. Lower levels typically occur during wet seasons and following tropical events. Now, the question that arose from this analysis is, why did we see such a profound decrease in specific conductance? Was this a result of climate change, or were other factors involved? So to answer this question, we decided to take a look at the components of specific conductance, which are the major ions. We retrieved the major ion data from our database for the 6 in-lake stations, and we summarized the concentrations of each ion by decade. We used 2 plotting methods to be able to differentiate any changes. Those plotting methods were the shoulder plots and stiff diagrams, which give us a visual representation of the ionic composition. The graphical shapes that these plots generate can provide useful information regarding dominant ion pairs and changes in ionic composition. The shoulder plot is shown here on the left, and it uses line plots to represent differences between cations and anions and identify dominant ion pairs. Stiff diagrams generate polygon shapes based on concentrations of ion pairs and can be used in making visual comparisons of waters from different sources. Below the stiff diagram section are several of examples of stiff diagrams. If you look at the top row on the left, you will see water that is dominated by sodium chloride. The middle shape gives you a codominance of calcium bicarbonate and sodium chloride, and the right shape shows you the dominance of calcium carbonate. At the bottom, I've provided a couple of examples of different types of waters with ion concentrations. So the bottom left plot or diagram shows you mean seawater, the ionic composition of mean seawater. The middle plot gives you the mean river water ionic composition, and the plot on the right shows you the ionic composition of mean South Florida rainfall. Now, the interesting thing is that rainfall in South Florida is very similar in the distribution of ions to seawater and to a sodium chloride dominated source. So this plot shows the results of our ion analysis. I'm going to start with the shoulder plots on the left. What we see is the decadal ionic composition or ionic concentrations in Lake Okeechobee. The top line here shows the 1973 to 1982 period. And we can see that this period appears to have a little bit more dominant sodium chloride presence. The bottom line shows the latter portion of our period, 2013 to 2020. And we can see that there is a shift from the sodium chloride dominance to more calcium bicarbonate dominance. This is also represented in the stiff diagrams here in the middle. You can see how the diagrams change in shape from more of a sodium chloride dominance down to more of a calcium bicarbonate dominance. So the shift in composition that we are seeing in the ions mirrors the observed decrease in specific conductance. And I'll show you that in the next slide. So there are several things that I've plotted on this slide. First of all, I'm plotting the time series plot for specific conductance that's shown in the top plot. And I've introduced a couple of ionic ratios. One is the sodium to potassium ratio and then a sodium to calcium ratio. Both of these ratios will provide us some insight as to potential sources of the shift in specific conductance that we've observed. On the top, I've provided the same stiff diagrams as in the previous plot for each decade, and the decades are identified as this alternating shaded and unshaded area. The numeric values that you see within each of the plots show the average and standard deviation for that particular decade for specific conductance, sodium potassium ratios, and sodium calcium ratios. Now, the interesting thing that we noticed was that during the 1973-1982 period, the sodium potassium ratios were higher and approached the mean marine ratio of 46. This suggests that during this period, a potentially more marine-like source of water was present in Lake Okeechobee. Potentially, this could have been a result of upwelling of connate seawater. When we take a look at the 1973 to 1993 period for sodium potassium ratios, we notice that generally these ratios are above 1, indicating dominance of sodium present in the lake. We also notice that there is a change in the concentrations around 1994, and the ratios now begin to resemble more freshwater type ratios, especially for sodium potassium. By the time we get to the latter decade, we see that the ratio is around 8, which is typical for freshwaters. So in summary, our trend analyses looked at 48 years of data. We found that water temperature and pH had increasing trends. The trends were not statistically significant. Dissolved oxygen did have a statistically significant decreasing trend, but the observed change, shown as the Sen slope, was not measurable over the period. Specific conductance, on the other hand, had a measurable significant decrease over the entire period. We also explored why this change occurred and discovered that there appeared to have been a shift in the ionic composition from more sodium chloride to more calcium bicarbonate source. The sodium potassium ratio suggested that the higher specific conductance levels observed may have been affected by a more marine-like source, possibly upwelling of connate seawater. The observed changes in both the sodium potassium and sodium calcium ratios appear to have occurred around 1994, and these coincide with the decreases that we see in specific conductance. Finally, this evaluation shows that the changes in water quality are affected by multiple factors that can exert a more complex influence on water quality and that hinder the ability to detect potential influence of climate change factors. So with that, I conclude my presentation, and I will hand over the presentation to our Master of Camouflage, Carlos Coronado, who will talk about observed trends in ecosystems.
Thank you, Nina. I'm very happy that I'm like that. Good morning, everybody. Thank you very much for attending this workshop. My name is Carlos Coronado. I'm a lead scientist in the Applied Sciences Bureau. Today, I'm gonna explain a little bit about the observed trends in ecosystem related to soil subsidence and estuary migration. This is a very important aspect, as Drew explained at the beginning of this workshop. This is one of the concepts, one of the ideas that here at the district we are interested in addressing. And the district has been working on these specific aspects of soil subsidence and estuary migration since the 1990s. Before understanding or explaining the trends, I'd like to explain a little bit what pit collapse is and or what we understand by pit collapse. This figure shows, going from the left all the way to the right, all the different steps that has to occur for us to observe any loss in elevation. The first panel on the left, it shows a very healthy ecosystem in which there is an active sink for carbon that is stored in the soil. Under these particular conditions, this system has a very positive increase in soil elevation. However, when any stress occurs, like in the panel here, we have two different types of stresses. Some of them are acute stresses that includes hurricanes, storm surges, and fires. And we have chronic stresses that includes hydrologic alteration, nutrients, loadings, and sea level rise. If any of those stressors affect the plant community, what we see next is a death in the vegetation. What happens when the vegetation dies in relation to the soil? So there are 4 proposed mechanisms that are trying to explain how the soil is lost in any coastal wetlands. The first mechanism is called pore space compression. And this, is a physical process mainly, and it just says that because of the pore space compresses, the soil loses elevation. The second proposed mechanism is the soil organic matter in the soil is destabilized due to a very increasing periods of inundation. Under these particular conditions of very long hydro periods, all the organic particulate matters that are in the soil start getting loose, and we lost elevation because of that effect of hydrology. The third proposed mechanism is parenchyma compaction, and it's just an explanation of all the pore spaces that exist within the root system. Once the plant community dies, all that pore spaces get compressed, and then we can see there is a loss in elevation. The last one is a biogeochemistry process accelerated by acceleration of mineralization processes because of there is an increase of loss of carbon due to biochemistry processes, we observe a loss in elevation. So what happens in these ecosystems when there is a loss in elevation? The last figure in this, the last panel in this figure, it shows that everything that was originally a marsh, healthy ecosystem becomes an open water. And that's the concept behind pit collapse and the mechanisms of soil surface, soil elevation. Next, as I said at the beginning, we've been measuring these processes here at the district since 1997 in different mangrove sites northeast of Florida Bay. We have very specific sites in this part of the system that we've been monitoring since 1996. And I want to point out that these monitoring sites are not the only one. We are part of a very larger network of sites where we've been measuring elevation soil changes, not only in this part of the system, but also in the West Coast and all the way to Rookery Bay. So we are part of a much larger network working together with USGS, University of Louisiana, Florida International University, and some other agencies. For this particular area, or monitoring sites are grouped in two different types of systems. The first monitoring site is a permanent inundated scrub red mangrove, and the second one is a frequently inundated scrub red mangrove. The difference between those two groups of mangroves is basically hydrology. The one on top has a more dynamic hydrology, the water flows, and in this one is where the water remains all the time there. Because of that, those mangroves are not relatively healthy relative to the ones at the bottom. So this is the area where we've been working for since 1997. How do we measure this process of sediment elevation? So the technique that we use is a sediment elevation table, SET, and marker horizons. Here shows in this figure, we show what the SET is, and it's just a sediment elevation table that the base goes all the way to the bedrock. And this pens, we use this one for very accurately measure how fast the elevation of the soil changes over time. This one is the marker horizons, it's a feldspar marker, and this marker helps us to see how much of new material is deposited on top of this marker horizon. The combination of both the feldspar marker and the set is what helps us to understand how these monitoring sites are dealing with elevation change. To show how we use this data, here have two hypothetical sites to show how we plotted the data. The one on top, it shows that both trends, the data coming from the SET and the data coming from the feldspar, they follow each other very closely. So there is very, very small distance between those two trends. And if we observe something like this, the interpretation is that for this particular site, the pit collapse or loss of the elevation is very small. In contrast, the figure at the bottom, it shows how the two different trends separate a lot over time. And the interpretation from this hypothetical figure indicates that this is a site where there is a strong loss of elevation or pit collapse. Here we have the clear definition of what we understand by pit collapse. Pit collapse is a specific type of soil subsidence, which is a process in which highly organic soil experience loss of soil strength and structural integrity that contributes to the decline of vertical elevation. So what the data that we've been collecting tell us? Here we have the actual results of since 1997 all the way to 2020, even though he says 2099, is what we've been observing. Figure on the left shows the results of the elevation change and soil accretion in the sites that we've been monitoring where are frequently inundated. And we have 5 different sites. This figure is the result of the data from 5 different sites. This figure shows that in a frequently inundated site, there is a really, really positive increase in elevation. And for the last 20 years, more or less, we have observed that is an increase in elevation at 3.9 millimeters per year and a vertical accretion of 2.1 with an increase of the soil expansion of 1.6 millimeters per year. This data for this particular site suggests that this type of mangroves are able to keep up with current sea level rise trends. In contrast, the figure on the right shows the mangrove sites that are permanently inundated. And in these particular sites, all of them, the trend is a very small elevation change, only 1.7 millimeters per year, and a vertical accretion of 1.9. Those 2 values suggest that the current sea level rise in South Florida, which is around 2.5 millimeters per year, this type of mangroves are not going to be able to keep up with sea level rise. Here, the important aspect of these values is how can we use the data coming from the elevation change and vertical accretion at more larger scale. So here is the result, just one of the different figures that are published. We published a paper this year, Dr. Frederick Clark, Chris Carlson, myself, and Dr. Carolina Moran. We published a manuscript in which we were trying to see at this landscape level in South Florida, how the different plant communities, each color represent a different plant community in these maps. And we wanted to see how the plant communities will transition from one to another or to an open water condition. So in this particular example, this figure on the top left is just observe what is the current condition in South Florida in terms of the vegetation, the distribution of the vegetation. Figure on the right, top right, it shows the results of how the plant community will transition if there is a sea level rise of 0.9 feet or 0.27 meters. Figure here at bottom left, it shows the same concept, but the change of distribution of the plant community if there is a sea level rise of 0.76 meters or 2.5 feet. And the last figure on the bottom right shows how the plant community will transition if there is a sea level rise of 1.1 meters or 3.7 meters by 2070. So by looking all the different figures going from the current condition to a sea level rise of 0.9 feet, we introduce in this map the accretion rates that we've been measuring in the field. So we say the highest accretion rate that we have observed in the field in our study site is 4.2 millimeters per year. And we multiplied this number by 50 because we want to see how the accretion will be in 27. So we only multiply 4.2 by 50. And we said that by 2070, the accretion accumulated by 2070 will be 0.21 meters. So we put this value into these maps, and by introducing the accretion rates in these maps, we see that having a very positive accretion, the transition of the plant community from one to another and to open water decreases. This figure shows, particularly the one in the middle, this figure in the middle shows the values that we see in terms of how much plant community or marsh or vegetation will convert to open water. This part, this figure shows if there is a sea level rise of 0.27 and an accretion of 0.21 by 2070, the transition from plant community to open water is very small. However, as if we have a sea level rise of 0.2076, the transition from vegetation to open water increases to 349. And if there is a sea level rise of 1.13 meters, the transition from vegetation to open water increases. This figure emphasizes very well the importance that accretion has on plant communities. In summary, we are showing here in the summary pictures of mangroves, both in Florida Bay, Northeast Florida Bay, and this is in the motherland area. So in summary, we see that increases in sea level rise and saltwater intrusion have induced release of CO2 from marshes. The collapse of marsh pit soils without sufficient freshwater input will hinder the landward migration of mangroves by reducing seedling establishment and below ground production, which is a very important process for organic matter accumulation. Second point is that the current and future responses of mangroves to sea level rise projections depends on the ability of mangroves to keep up with sea level rise. In Southern Everglades, mangroves can keep pace with sea level rise with current levels of sea level rise, and it will be more difficult for them if there are sea level rise values between 4 and 0.6. And finally, our modeling from the manuscript that we published indicates that transition to open water by 2070 will occur if accretion rates are not enhanced. Finally, everything that we've been working on sea level rise and how mangroves are dealing with increases in sea level rise are already in our story maps. And this is something that you will be able to see after the end of this workshop. Thank you very much for your attention. And next, it will be Dr. Carolina Moran to explain more about the sea level rise resilience. Thank you.
Wow, you can see that we have extensive work that was developed during this 1 year since what we present in the beginning of 2021 and what we are presenting today. This technical leads really just summarizing what we saw here today. We were not only able to read, try to really interpret the trends, to confirm the significance of what we are seeing in terms of advanced statistical analysis, and also begin the important step of correlating with influencing factors. There are many things that are happening out there beyond just trying to capture what we seem to interpret as a climate change. And that's why we have science to really help us to understand and test this out. Those are not very simple assumptions that we can make when we see a trend. It's very evident that what we are showing here today demonstrates the importance of looking at all this data. And I need to also say that we have other technical leads that have been producing the same level of efforts to the remaining metrics that they were not presenting here today. As you can see, just by looking at those 4 experts here, we exhausted, like we are almost like overwhelmed with the amount of information that we share here today. So we've just decided that there was a limit, and we brought the results from these 4 here today, not to mean that we have other metrics that are as relevant as this one. So I really would like to take this opportunity to thank for the work of this technical leads involved, the ones here, the ones that are not here today. We have Dr. Tibebe Desalane, we have Dr. Alain Ali, and we have also Christine Carson that are doing extensive work with some additional metrics. So, and not only them, thank for their work, but also thank for the supervisors and the bureau chiefs who really supported us in shifting the priorities among so much other relevant work that the staff here, that the district does. So everybody here is involved in a series of additional efforts, and they are putting this on top of what they already do as part of their roles. So thank you everyone. Thank the chiefs, thank the supervisors to allowing us to get to where we are today. In addition, I really have to say that we have our IT team. Within the IT, we have the geospatial team, who is really the pillar to bring all this information together and make the links to our existing database so we can have access to real data. So really the goal of having this hub and putting this together is not to have all this information in a report. They are helping behind the scenes to really put all of this available, making the access to real-time data so people can download the data, can access more quickly through our portals how to get to where we are. So with that, I want just to move quickly to next steps. So we are really working with our GIS team, our geospatial team, to bring this full content respective to all the metrics to the Resilient Hub. We have a few there already, and we are bringing more. We are also completing the automation, so there is no real-time data yet in the hub. We are working to make the link to the Behind Insights. This is a very robust tool. If you didn't have time to really look at what we have in the Behind Insights, please take your time. It's already a very comprehensive tool that we are facilitating more and more the way people can access and understand the data that we have there. And this brings a new link to the Behind Insights just so that people can have access to the data that we are plotting as a long-term trend here, also via the Behind Insights, and really making the connection with this real-time data. We will be continuing to publish this technical analysis and scientific resources as part of our South Florida environmental resources. There is a lot in terms of science for us to understand, to be able to make assumptions. So keep your eye also on those chapters that we are bringing to the South Florida environmental resources. We have a calendar for next year already, bringing a few of the additional metrics. And of course, revisiting some of the findings that we are presenting and complementing the analysis. As part of this process, we also look at some data monitoring needs or enhancements on the way we collect the data to be really able to look at those trends. So some spatial quality, spatial distribution quality and frequency that can help us to evaluate those trends. And we receive several comments as another next step on suggestions for new metrics. We had an initial list that was larger than what we are addressing. But yes, we will be addressing as we see the availability of data and as we see resources that we can look at those additional metrics. So thanks for all the recommendations that we received from the comments on incorporating new metrics. And yes, we will be looking at the databases. We will see what resources are available for us. And we will, it's a continuous effort. So as we see this, that we can advance with incorporation of new ones, we will definitely follow those steps. And then the next step that we have here, as you know, in the report, this is a phase one when we look at observation. So this is not, we're not making assumptions. We are looking at data that we monitor. And we understand that this will also lead us. We have a lot of planning projects that really depend on us making assumptions about the future. So, and it's not a very simple process. Even though we see sometimes a lot of like very simple linear extrapolations and sometimes exaggeration on the way we approach this, we really need to understand how we depart from observations to projections. That is another scientific process that needs to be embedded in the process before we really make those assumptions. So that's why we are really careful here to understand what's happening and how can we work. And I'm bringing here the rainfall case as one example. We initially thought about bringing some rainfall discussions today. We have some new databases that I'm going to talk a little bit about but it became very evident that the rainfall case really deserves a workshop for its own. We have extensive analysis. We have our technical lead that is leading the work, but not only him, we have additional experts in the agency that have a lot to contribute. So we will really begin to discuss these next steps in some projections in a separate workshop early in 2023. But what we have in the hub today, and I am asking permission here for the technical lead to just share a glance. So you can just briefly address a little bit of the curiosity. What we have today in the hub is those trends that we identify in our observed data for rainfall. We organize them by region. We're going to explain all of that, but rainfall is a very characteristic type of data in where when we look at individual stations, there is a lot of noise. So there was a recommendation from our experts that we should look at regions in a way that we can capture better those trends. So we did a regional frequency analysis for the rainfall. This is what we have in the hub today. And what we see, I'm using two examples here. On the left, you're going to find some rainfall trend analysis done on a month-by-month basis. So again, this is data, observed data for all the 14 regions that we have. Those are the same regions that we report in our South Florida environmental report. So we organize the data by those regions, and we can see here plots that show trends, upward trends. For instance, we got this month of August here. And some of these trends, the ones that are showing red, where we have significance, statistical significance in the trend. So just to point to you, we also have October, for instance, as a month, the ending of our wet season, where we are seeing a decrease. So it's not only increased rainfall, we have seasonality issues and we have seasonality questions. And that's why it's important to really dig deeper in the data to understand what we want to say and to see how we can interpret all those results. We also look at wet season here. Those are the images on the images on the right side. And again, we see for some of the regions some upward trend, significant ones in red. And we even see one region that is showing a significant decrease for rainfall in that geographic region. And yes, we have been working to look at future rainfall too. We have a partnership with the USGS to look at some global climate model data sets so that we can start understanding what's out there and how can we read future rainfall in Florida. As I mentioned, we're going to have a workshop early next year to talk about rainfall and not only show the observed, but really discuss what we have already produced in partnership with the USGS. We receive a data. The first delivery from their contract with us was what they call a data release. We have a portal with some data available there. It's a public website you can access here. But what we saw as an agency is that there is clear need for us to review, to understand how we want to incorporate this data. There is extensive amount of data here. We almost overdid the way we are looking at the data. And so what we are doing internally with our experts is really to review what's there. How can we bring this to our planning purposes, our projects. At a first glance, we look at like perhaps we have different global data sets there. We are looking at perhaps using an ensemble of those data sets as an initial recommendation, just to give you an example. It's also very clear that we want to show the data for regions, hopefully the same 14 regions. We are working on the same 14 regions for the South Florida Environmental Report. And to again have the consistency in the way we report things and also be able to read all this information. And this is what we are discussing internally, how we want to see how it's most useful to our processes. And when we have a final release from USGS, we are hoping that we can also have some initial review from our internal teams that will help really partner stakeholders to access this data in a more informed way. And we welcome comments. We welcome feedback in this initial stage where we're still reviewing the data from partner stakeholders. Please reach out if you want, and please spend your time if you want to take a look on what we have already in this USGS data portal release. With that, I'm nearing the end of the presentation. A lot of what was shared here today, and again, our technical leads that were not here will be presenting at the 2022 UF Water Institute Symposium in February. So join us there. We have some of those presentations there in some of the panels, very interesting discussions that we're going to be advancing there too. And with that, I will invite Yvette to moderate the Q&A session. Thank you.
Great, thank you. We will now move on to the questions virtually. If anyone has a question, a technical question related to today's discussion, you can do so via chat or by submitting a card if you are here in person. Dr. Moran, I have no hands raised, but we do have questions.
Yeah, we have one more round to see if any person in the audience would be, do we have any comment cards or anything, question cards from the audience?
I have one that just raised their hand, Alberto Aran.
Okay, no, I mean from the, let me just clarify quickly, the Q&A session, we are going to be getting questions from the audience in person here or via written comments in the chat for in the virtual Zoom meeting. So any questions from the audience? One more call. Yes?
Hello.
Want to come to the, yes, we have there because so that everybody in the meeting can also hear. Thank you.
I have a question for Carlos about the wetland and sea level rise. Is this average or it's changes across the district in, for example, in Biscayne Bay versus Florida Bay, or the one that you showed the bar chart that showing with the different scenarios of sea level rise? Is this changing in average or in some area is worse than the others?
So let me see if I understand very well your question. You are asking if sea level rise is different from one side? From
yes,
one?
exactly.
No, the sea level rise that we are observing is coming. There are three main gauges that we are using currently. One is the one in Key West, another one is in Vaca Key, and another one in Virginia Key. The values of those three different gauges are different, but they are different because the time frame that they've been measuring sea level rise is different. So if you have a very short term measuring sea level rise using those gauges, the value that you get is relatively different. It's much higher in Virginia Key because it has a short record of data. The largest record of data is the one in Key West, and is the one that I mentioned, 2.5, more or less, today.
Yeah, and the bar chart that you showed, so was it for one of the specific one, or it was average for all the three sites? Because it shows that the wetland and then compared to the sea level rise, the change. So I didn't get which one.
Can I look at the figure to answer the question?
Do you want to see or do you want to follow up? Maybe. Do you want us to go back to the slide or perhaps you can follow up in
Yeah, I can follow up with him.
are you okay with that?
Yeah,
Yeah, so we don't, yeah. Otherwise it might get a little bit complex to move forward. Thank you. Any more questions from the audience? Okay, if not, we're going to move to the Q&A session from the Zoom. We have already a few questions here. I invite Nicole to join us and present those questions. And if you are participating via Zoom, please use the chat function to submit your written question.
Thank you, Carolina. The first question we have is for Corinne Smith. This question is from Catherine Higman. And here it is. In the plot showing the daily stage for the Snapper Creek, it looks like the headwater stage in blue has been slightly lower in recent years. Why is that?
In discussions with operations, they have shifted where they move the water in the South Dade system. And so that's why you're seeing that change.
Thank you, Corinne. Carolina, this is a question for you. This is from Aaron Deddy. Can you provide this data, particularly the water quality data, to Tim Rack at DEP for review in stormwater rulemaking processes? The TAC seems to be looking for ways to integrate good data sets into the rulemaking effort in terms of climate, sea level rise, and flooding. Their report is very much lacking on this.
Thank you. So we do have water quality data presented here, but please, we have to note that this is Lake Okeechobee data. We have looked at additional data sets that we could look at. Water quality, that's a very complex data set. We don't have very robust additional data sets that we could expand district-wide yet. So I think that's important just to note that this water quality data is from Lake Okeechobee. And yes, we had an initial discussion with our representative that is part of the technical group with FDP on this water quality stormwater rule. And we are sharing the data with them, and anything that we can make available to the discussions, we will, of course, provide to them.
Excellent, thank you. I have another question for you regarding sea level rise. So here, this question is from Valentina Kakia. Have you done any data analysis and interpretation of canals and sea level rise in the canals that are adjacent to Biscayne Bay?
Yes, this is one of our metrics. We have a metric that is called sea level rise. It's really the tidal elevation in our coastal structures. Our technical lead is Dr. Tibeb Desalagne. So yes, the answer to your question is for the coastal structures that are there, including not only Biscayne Bay, but all along our coasts, both east and west coast. We have data and we have been tracking this. This is part of our metrics. And it's being brought to the hub next, and it's already available. It will be available as part of the SVR chapter this year, and we have some data already in the report.
Kevin, this question is for you. This question was submitted by Catherine Hagman. For the changes in evapotranspiration, did you see that the primary driver of the change was solar radiation? Could you describe that in more detail and what has been changing?
In hydrology, in ET estimation, it's well known we have 4 parameters we usually look at: the solar radiation and the relative humidity, air temperature, and wind trend. And all our data, actually the data is from UIGS, shows the highest correlation. The R square is 0.76. In environmental size, this is pretty high correlation. And it shows this is the number 1. The second one is relative humidity. The R square is down to 0.11. you can see quite a difference. And also we renewed a lot of literatures for this study. And the most, they also show, I mean, from other studies, they also show the ET estimation that is most contributed by solar radiation. And also through the personal experience, you also can see if you get your clothes wet, if you put, if it's overcasted day, probably it takes a long time to dry. But if you end in the sunshine, it dries quick. So this is in the personal, experience from life. And then this also proves. I hope this answers.
Thank you, Kevin. The next question is for Carolina. This question was submitted by King Long Wu. Extreme weather patterns in drought and rainfall have become more common in the world. Are we going to conduct some research in this area?
Yes. So as we will have a workshop early next year that will be focusing on rainfall. We share a little bit of the data with you today, and I know we focus on the wet extremes. We have done some initial analysis on dry extremes. That's definitely an area that we need to also add additional work. But yes, you're right. We have some initial results already pointing to this changing in rainfall patterns. We also are evaluating additional global climate model data sets, understanding how they fit, how they represent our weather patterns in Florida. And yes, this is an active area of research, and we'll be looking forward to share this early next year with you all.
Thank you. This is another rainfall question for you, submitted by Joe Horowitz. Many local governments use 500-year rainfall metrics for setting building and flood standards for critical structures. Might you discuss why this is not included in the new rainfall projections?
Yeah, we have actually 1 in 100 years. We have actually evaluated all the return periods. This is really part about the work that we are going to be sharing details early next year. I believe what you saw here today was the data, summarized data for wet season and 1 month in terms of trends, observed trends. But we also did the same effort, and we have it all in the South Florida Environmental Report. So we look at 100-year extremes. How is the trend behaving? We look at 25-year extreme, and this is all there. We have the plots, the extensive amount of charts that are included in the South Florida Environmental Report that can really talk about that. So we have, for all the wet extremes, we have data. And as I mentioned, we still are pending some data to look at extreme dry that we're going to be bringing as part of next efforts.
Thank you. I have 2 questions now for Nanad regarding water quality. The first one is submitted by Antenne AB. Water quality. Is there any evidence for upwelling of connect water? Is there a plan to explore this further? What is the cause of upwelling, and what does this change in the future?
Well, I can't answer the question as far as what the evidence of the connate water coming up, but based on information that I've gotten, there was a lot of construction activity in the 70s around the lake, and the area in the southern portion of the lake and below the EAA extending out to the Waxahachie National Wildlife Refuge has a large region of relic seawater that's trapped in the rock. And with the activity that occurred in the 70s, there is a very high probability that some of that connate water had migrated into Lake Okeechobee. After that period, what we're probably seeing is a flushing of that high sodium chloride water out of the system. So that's really what's going on. As far as the evidence, there's a lot of USGS studies that have looked at the groundwater under the EAA, under portions of Lake Okeechobee, and in the ensuing canals. And we know that there's a high chloride content in the EAA canals, as well as sometimes seeing that content coming up in the canals around Water Conservation Area 1 under extreme conditions where we do not have inflows coming into those canals, and we have a dry season or a dry period, we can see potential connate water coming in. There was a study done for DEP looking at understanding sulfate influxes, and they did notice that under dry conditions, sulfate values coming into the canals surrounding the Loxahatchee National Wildlife Refuge had some similarities to marine water when they looked at sulfate to chloride ratios and sodium to potassium ratios.
Thanks, Nanad. This next question is also for you. It was submitted by Edward Carter. Are the Okeechobee ion differences due to pollution runoff reduction or changes in groundwater levels? Do the groundwater levels have similar ion content?
Again, typically, the northern portions of Lake Okeechobee groundwater is more carbonate enriched. The southern portions have the sodium chloride. I don't know if it's pollution, as you would call it. I don't think it's anthropogenic. I think that maybe anthropogenic activities may have induced the movements, but I don't believe that it's an anthropogenic result in the shift of the ions. I think it's basically the connate water exists there, and whatever activities may have occurred in the 70s induced that connate water to migrate into the waters of the lake.
Thank you, Nanad. We have another question here for Carolina, actually, also submitted by King Long Wu. Monitoring is very important in understanding climate change and sea level rise. I'm sorry, I think that this question is for more for FDP, not part of the panel. I will read it, not necessarily expecting an answer. Monitoring is very important in understanding climate change and sea level rise. Is FDP and the resiliency program going to provide more support in this aspect? You can provide some.
Yeah. We are working in collaboration with FDP in advancing those efforts that we have here. I believe we got our Deputy Secretary opening the remarks, and happy to follow up with them to provide any additional information. But thank you.
Thank you. We have a question for Dr. Coronado. Here it is. You say that mangroves can't keep up with 2.5 millimeter sea level rise. What is the health of the ecosystems you're monitoring? Are there any eastern oysters that are growing in these areas that could help build more lands and possibly meet or exceed the 2 millimeter per year levels in accretion? Are any areas studied focused on areas like this?
Yes, thank you for the question. No, I think one of the important aspects of this part of the system is that all the peat that has been accreted in that area is highly organic. It's not coming from outside the system. It's produced entirely by the mangrove community. There is nothing coming from outside the system. That's why I don't think oysters will have a very significant effect in the first place, because in the area where we've been monitoring elevation change, oysters are not important part of the system, in this part of the system. They are more important in the west coast of South Florida, but not in the northeastern side of Florida. So to really emphasize the mangrove ecosystem where we've been working, everything that we see on a healthy mangrove ecosystem to really keep up with sea level rise is gonna come from inside the mangroves. If we have a very healthy mangrove community, they will be able to keep producing more organic matter, and probably will be able to keep up with sea level rise. However, the important here is hydrology. The district, one of the main missions of the district is to restore the flow of fresh water all the way from the north, all the way to the south. The input of this fresh water into this part of the system will really, really help the mangrove ecosystem in this area to be more healthy and produce more organic matter and maybe being able to keep up with future sea level rise scenarios.
Thank you, Carlos. This question is for Dr. Moran. For the rainfall trends, did you look at changes in rainfall intensity?
Yes, it's evident that we need a workshop to talk about rainfall. So yes, we look at rainfall intensity. This is the main way that we are just looking at this. So for both observed rainfall and for future projections, we are looking at intensity of rainfall and looking at the different return periods.
Thank you. We have a question that is a little bit open-ended, but I think our technical leads can provide, maybe Corinne especially, and Dr. Moran can provide some insight. The question was submitted by Valentina Katka, and it is, are you evaluating data in the watersheds of Miami-Dade County?
Yes, so we are evaluating data district-wide. We have data for all the areas that we have that within our boundaries where we have data that is, as we mentioned, long-term observed data, consistent, like continuous monitoring, and it includes areas in all our counties, the 16 counties within our area.
Okay, we have one more question. This was submitted by Alberto Aran. It is a follow-up question that says, will future fresh water flows change the salinity conditions to help oysters make a factor in these systems? This is for Carlos. I should have said that.
Can you please repeat the question?
Yes, will future freshwater, I'm going to say this is in terms of restoration of freshwater flow. How will that impact salinity conditions to help change the ecosystem?
Yes, thank you again for the question. Yes, we believe from what we have seen, measuring also salinity in the pore water in this part of the system, is that when there is an input of fresh water, there is a decrease in the pore water salinity. And that decrease in the pore water salinity really is a really good condition for mangroves to become more productive also. Again, the concept of oysters in this part of the system, I still don't see it because they are not an important part of in this part of the system. Maybe if we were talking about the west coast of South Florida, let's say 10,000 Islands, Rookery Bay, that part of the system, oysters are a much more important component of the system, but not in the area where we've been working for the last 20 years.
Thank you, Carlos. I have no more questions, but 2 comments to share. The first one submitted by Joe Horowitz, directed to Dr. Brooks. Thank you, Dr. Brooks. We recommend that the tribes be recognized as eligible for state resiliency funding along with our local government and regional partners. Thank you. The next comment was submitted by Michael Zignerski. It is great to see the South Florida Water Management District dedicate so much expertise to these valuable analyses that will help guide not only the South Florida Water Management District in beneficial water management projects, but also local municipalities and drainage districts in alleviating current issues and flagging concerns to help better plan and address the future impacts of climate change on our interconnected and interdependent systems. This completes the Q&A that we have received.
Great, thank you. So should we move to our public comment session? I believe Yvette will be moderating, and we can, Yvette, do you want to open up for public comments, please?
I have no hands raised.
Second?
We'll give it a few minutes, but I have no hands that I've raised.
I received a comment in the Zoom chat. That is, congratulations on your scientific work. Very interesting and great scientific interpretation. Visual products were great. Love to see that more women are working in the environmental field as leads in science.
Okay, with that, we end our public session. I would like to thank everyone. I would just share with you quickly that we share a lot of what our findings on what will drive some of our actions, and we are doing significant efforts already this year to start action, to really motivate what we should do in terms of when we look at those observed trends. We have, for instance, in this year, launched our first sea level rise and flood resiliency plan, looking at our flood mission. So really including several projects and priorities that we need to be advancing in terms of infrastructure investments in our area. We also developed a tool that helps us to look at future, so flood damages and how can we bring those flood damages as part of cost benefit analysis to each of our projects. We're going to be launching the tool also in the data available for you and the exposure database that we did early next year. In terms of looking at water supply, our next mission, we are beginning to work to expand our groundwater modeling to really assess water supply under future conditions, more to come. This is going to be part of our Lower East Coast planning efforts in 2023. And if you have not heard about EMA, I suggest you do. Carlos talked a lot about the Everglades and peat subsidence. We have a project that we are advancing in partnership with the Army Corps that is really looking at how perhaps we can enhance peat accretion, soil accretion in the area to really deal with those resilience issues. So we are really pointing to a lot of the solutions that we need to not only adapt. So I would say for those climate metrics that we have not a lot that we could do in terms of changing rainfall. For instance, we know we have to adapt. So there is action, substantial action that we are doing in terms of adapting to that, and also significant efforts that we are advancing to mitigate our resilience metrics to really go ahead. With that, I would like to, we have one slide there, happy holiday slide in red. I'm bringing here a very special image from my son. So in the name of the district resiliency team and our colleagues from the various district teams and partners that have really embarked in this resilience team, in this resilience journey with us, we really want to wish you all a happy holiday. And we have a thrilling pathway ahead of us, and we'll be making sure that resiliency is leading our way. So thank you everyone for participating in today's workshop.
Thank you. We're adjourned.